But the other paper, which was actually a paper that was written before, they showed that in case your utility function is not concave, so it is not concave, then the core is not necessarily always non-empty. So it can be that you have an empty core. Okay, too much about the literature. What we will do is we will actually formulate our game as a market game as well, but not with the concave utility function, but with a convex concave utility function. Okay, here it is. So we're doing some mathematics. We want to model a certain situation, so we need notation for our model. So let n be the finite set of players, and that set of players are, for example, countries or geographic regions. Yeah. And every country, every player has a certain number of inhabitants, certain number of initial vaccines. That is the initial situation. After that, we're going to redistribute the vaccines. And there is an S-shaped return function. I will come back to that later. So that's this convex concave utility function. So how should you read all of those letters? Well, it works as follows. This S-shaped return function, what is the input of this function? It is the fraction of people that get vaccinated. So you divide the number of vaccines over the number of inhabitants. Yeah, that's the input for your function. And the output of this function is your monetary health benefits that you get per inhabitant. So if you multiply it with the number of inhabitants, then you get the monetary health benefits. Okay, I hope that this notation is clear to you. So this is the S-shaped return function. It is an increasing function. Here are all the mathematical definitions, why it's called nicely convex concave. Well, it is an increasing function. So in other words, the more vaccines you have, the higher your monetary health benefit is. Makes sense, huh? And if you look at it over here, so this is the convex part, and then it becomes a concave part. It's all the time increasing, but in the beginning, it doesn't increase a lot, then it increases a lot, and then it decreases with increasing. And why is that? Well, in the beginning, when you start vaccinating only 1%, 2% of your country, then the monetary health benefits are not that much. But the more and more people you vaccinate, the bigger is the group immunity. And that's where we have the shape from. Okay, now you're wondering, okay, but it all depends about how you model your situation, etc. So is it actually the right way of modeling it? Well, here is a very long mathematical lemma. And it says that if your epidemic is modeled with the SIR model, okay, Noor, can you pose the fourth question? What does SIR mean? What does it stand for? I think most of you have heard about it. It is the SIR model is basically a model about how to model an epidemic, and it is done by means of differential equations, where the S indeed stands for susceptible, the I for infected, and R for recovered. So susceptible is the number of people that can get ill. Infected, the R are the number of people that are infected, and R the number of people that are recovered. Okay, so this lemma states that if you model your epidemic in this way with this model, then indeed the monetary health benefits indeed follow this S-shaped return function. So it makes sense, our model. I mean, this SIR model is a very well used model for modeling an epidemic. So this convex concave return function actually makes sense. Just to let you know that it's not some weird function that we just came up with. It makes sense to model the situation. Okay. So here we have our game formulation. Again, we need to define a value for every coalition. A lot of notation over here, but what does it say? We want to maximize the monetary health benefits of all the players within the coalition. So we want to maximize this, such that we satisfy our resource constraint. So in other words, what we have on the left-hand side is the number of resources that we're going to use. And on the right-hand side, the number of resources that we initially have. And of course, the number of resources that we use cannot be more than the number of resources that we have. Yeah? So we have smaller or equal over here. For the DKE students among us, it is basically a knapsack problem with S-shaped return function. Doesn't matter, but it's NP hard. What is NP hard? That also doesn't matter, but it's very difficult. Let's say it is very difficult to find an optimal solution of this problem in a reasonable amount of time. If you calculate it with the computer, of course, when your coalition S is small, it is only 1, 2, 3, 4, 5 players, etc. It's still doable. But the larger your coalition gets, the more difficult it is to calculate this problem. Okay, but that's going to be difficult. I mean, if calculating the value of one coalition is already difficult, what about calculating the value of all the possible coalitions? So of all the numbers in our table, and it's going to be even more difficult. Okay, so we want to say something about the core of this game without actually calculating the values of the coalitions. But how can we do that then? How can we say something about the core if we do not calculate all the values of the coalitions? Okay, first, to make it even more clear why cooperation is important, let's look at this example. So we have 3 countries, easy. Here's the S-shaped return function. So here's the number of people that you can vaccinate, and here is the monetary health benefits that you get. Suppose that this is the initial situation. What is then the joint utility, the joint profit? Well, you simply sum up, what is it? 0.45, 0.45, 0.45. That is everything that you can get in the initial situation. But can we do better off? Can we somehow make use of this very steep part in the S-shaped return function over here by redistributing the vaccines? Can we improve our 0.45 times 3? Yes, you can. So in total, we have, let's say, 1.5, of course, it's a fraction, 1.5, I don't know, million vaccines. If we distribute it in this way, yeah? So what we basically do, country C gives away all his vaccines, yeah? We give it to country A and country B. Hey, but then if we look at the monetary health benefits, that is much more than in the initial situation. So it is actually better that country C gives away the vaccines. And then in total, country A, B, and C are better off in total. But country C is worse off, and country A and B are better off. So country A and B need to pay some money to country C for the vaccines. But how much do they need to pay? That is the question that we want to answer. What price is fair for this situation? So, and is it actually possible? Is it actually possible that we find a price such that A and B want to buy the vaccines for this price? Yeah, so the price shouldn't be too high, and that country C wants to give away the resources, the vaccines. So the price shouldn't be too low. Okay. Well, when is cooperation possible? Of course, there are many political and organizational reasons. So there can be reasons why countries do not want to give away their vaccines to another country. Of course, I understand, but let's forget about that for the moment. You also have the problem of transportation of resources. Is that actually possible to transport the vaccines, or is it then already too late, or is it too costly, etc.? Let's forget about the two things. When you're making a model in mathematics, you should make your life, the world, a bit more easy. Otherwise, you cannot draw any conclusion. So let's focus on this fair division. Yeah. And here we go again. When is it fair? If it's efficient and stable. This is the definition of the core definition that I gave before. Okay. Is the core always non-empty? Or can it also be that the core is empty? So in case the core is empty, you cannot find a fair price, right? Okay, look at this situation. This is the S-shaped return function, very complicated function, but I draw the function over here for you. This is the number of inhabitants. Let's say it's 1 million, 1 million, 1 million. And this is the number of vaccines. Yeah, of course, it's all a fraction, so do not think too much about the 0.2, but just multiply it with a certain number and then it makes sense. How does the game look like? Well, it's as follows. Is cooperation possible? In other words, is the core actually non-empty? Well, if you simply divide this number of the value of the grand coalition, if you simply divide it by 3, then you see that every coalition agrees with this number. Well, players 1, 2, and 3 individually, of course, they will agree because they get at least 0. 1 and 2 together, do they get at least this amount? Yeah, sure, this is much more than the value over here. So we find the core element, so the core is non-empty. Yeah, so we can make the 3 players cooperate together. But suppose now that I slightly change the numbers. Instead of 0.2, I make it 1 over 3, 0.333. And that completely changes everything, because suddenly the 2-player coalitions, they are over here. Suddenly they go from the 0.4 over here, so almost nothing, to a lot over here in the figure. And this increase in the initial amount of resources actually makes the core empty. Simply look at the constraints over here. Yeah. Okay, so the core becomes empty. What does it mean? It means that, okay, in the optimization part, okay, we can do better off by redistributing the vaccines. But we can never find an allocation. We can never make every player cooperate. So then that is what we say, cooperation is a delicate matter. You can make a joint allocation of the resources that is better off for everyone together, but you cannot give this incentive to the people to give away their resources. So in this case, of course, it's better to cooperate, but in practice, it will not happen because you will not make them cooperate. So that is why this question of the core is empty and the core is not empty, that is why it is so important. Okay, here we go to market allocations. And those allocations will be very interesting because they're quite often core elements. What is a market allocation? Well, first of all, an allocation of in our game can be written as the sum of 2 things. What we have over here is the monetary health benefits. Yeah, so the health benefits that you get in the optimal solution from your allocated number of vaccines. Yeah, so here we have the monetary health benefits. What we have over here is the profit or the cost from trading the vaccines. So if you sell vaccines, if you give away vaccines, then it is plus the amount of vaccines that you sell, that is the part over here in between brackets, times the price, times what you get per vaccine. If you buy resources, then this number becomes a negative number. namely the amount of vaccines that you buy, times the price. And that the costs from buying the resources need to be subtracted from the health benefits in order to get your allocation. And now here you see that this P, it is dependent on I. And what do I mean with that? I mean that the price can depend on the player that you are. So maybe Germany pays a different price for the vaccines that they buy from Italy than the Netherlands does. That is possible. But we will look at market allocations. And in market allocations, we assume that every country buys or sells their resources for the same price. So let's focus on those market allocations. So it's your health benefits plus the part that you get or give away for selling or buying resources, where the price per resource is always the same. And the question is there a P such that the market allocation is in the core? So can we find a price such that this allocation is a fair allocation, that everybody agrees with this allocation? Okay, interesting. So we will focus on those market allocations and finding the price. Well, if it is a core element, then it needs to be efficient. Well, that is almost always true. Only in very weird cases that you have a tie, then it's not the case. So let's say that efficiency, believe me, that is almost always satisfied by construction. But stability, it is not. So you still need to look for what value of P is your allocation stable. Okay, let's focus on that. Here we have another situation. Now we have our function. You have the 3 countries with their inhabitants. You have the number of resources, and then this is the corresponding game. You can show, we will not do it over here, that the core is non-empty. But we can also show that there is no market allocation. So we can find a fair allocation, but in this fair allocation, people have different prices for their vaccines. Okay. How do we see that? Well, in the optimal solution, we simply give everything 1/3 of the total amount of vaccines. So this 1.75, which is the sum of this, over 3. And then when you look at country 1 initially had 0.1 resources. Now it has 0.58. So it bought some resources. So in other words, country 1 has an upper bound of the price that they want to pay. Country 3 has to, country 3 has to sell some resources. Initially they had 0.65, now 0.58, yeah. So they give away resources, so they have a lower bound for how much they want for their resource, for their vaccines. They want at least this amount for their vaccines. And if this upper bound, yeah, if that is lower than this lower bound, so they want to pay at most 3 euros and they want to have at least 4 euros, this is not possible. And thus we cannot find a market allocation. So in this example, this is how you show that there is no market allocation for this specific game. Okay, suppose that we have only 2 players. So you always need to start with an easy case. What is so convenient about 2 players? You always have a seller and a buyer, yeah? Or the amount of resources stays the same, but then nothing happens, then there is no question to answer. You always have a seller or a buyer. Either the vaccines go from here to there or the other way around. Maybe not all of them, but part of them. Then we showed that we can find a certain interval, basically this lower bound and the upper bound, so the lower bound for the seller and the upper bound for the buyer. And we can show that this lower bound is always smaller than this upper bound. And thus a market allocation is always possible. Doesn't matter what the input is, as long as you have 2 players, there is always a market allocation, and this market allocation always belongs to the core. Okay, interesting. So in case you have two players, then cooperation is always beneficial. They will always agree with this cooperation. Is that true in general, actually? Is the core always non-empty? Well, for this, we will look a bit more closely to this S-shaped return function. And now it might become a bit technical, but as long as you have the intuition, I think you can understand quite a lot of it. And for this, we need some new notation, but I will explain it by means of the figure. What does this very complicated function do? It basically gives you the average slope so far. Yeah. So here you have your S-shaped return function. And what is the average slope so far? You basically take a point over here and you draw a straight line from here to there, and that is your average slope so far. So in the point over here, this is your average slope. So you take a point, you look at the point on the graph, and you draw a straight line from this point to the origin. That is the average slope. Yeah. So this is basically how much you got on average per number of vaccines. Okay. And then there exists a unique number, I call it F tilde. And this F tilde is somewhere on the horizontal axis. It is some amount of vaccines. Yeah. And this F tilde is unique. It is the point where the slope of the function is exactly the same as the average slope. Okay, I hope you're still with me. And it is exactly over here. If you draw the slope of the function, and it's exactly the same line from here to the origin. Yeah? That is not the case over here, because the average slope is somewhere something like this, and the slope over here is something like this. Yeah. So this unique fraction F tilde is where the slope of the function is exactly the same line from this point to the origin. And there's only one such point because it's an S-shaped return function. And this F tilde, it's the dose optimal vaccination fraction. And why do we call it the dose optimal vaccination fraction? If you take more resources, if you take more vaccines, of course, your monetary health benefits will increase, but the average health benefits will decrease. Yeah. And also if you take less, then the average health benefits will also be less. So this function at this point is the optimal if you look at the average health benefits. Yeah. Okay. Yeah, I think that is everything that you need to know. As long as you understand this point, F tilde, and as long as you understand why it's the dose optimal vaccination fraction, then it's good. So now we will look at the following situation. Suppose we have a very severe shortage of vaccines. Yeah. And what do I mean with that? None of the countries can reach its dose optimal vaccination fraction. We have so few resources that even not one country can come to this dose optimal vaccination fraction. Suppose that that is the case. That's why we call it a severe shortage. There is a really big shortage of vaccines. Then, again, it is an OR game. So we first want to know what is the optimal solution. So how do we need to allocate the vaccines? After that, we will look at the game theory question. How do we divide? How do we divide the money, actually, in this case? So first, the optimal solution. How should the number of vaccines be allocated? Well, you simply give it to the person that has the highest average slope. Yeah? The higher the average slope, the more you get per resource. That is simply the idea. Yeah? So we give it to the player for which the average slope is the highest. And since we have severe shortage, nobody will get to the point F tilde. So this is the optimal solution. Well, this is the first theorem of the paper. Of course, there is a very long proof. Just to give you an idea of the proof, we prove it by means of contradiction. We say, okay, suppose that this is not true. What happens then? And then you come to a contradiction. So you know that it should be true. Then the core. Then we can conclude in the second theorem that if we are in this severe shortage, then this is indeed the optimal solution. We give everything to one person, namely the person for which the average slope is the highest. And if we use this slope, this average slope, as a price, then this market allocation is in the core. It makes sense, huh? Because this person who gets all of this, of course, he doesn't want to pay more than this average slope, because then the price is higher than what he gets for it. So he doesn't want to pay more. Yeah. And in the same way, you can argue that the sellers, they also do not want to get less for their amount of money, for their vaccines. So that's why this average slope, it plays such an important role. It actually determines the price of your market allocation. Oh, but if you have those two theorems, then we can also conclude that the core is always non-empty in this case, right? Because we found the core element, namely this market allocation. So there's at least one core element. So in this case of severe shortage, cooperation actually makes sense, and we can find an allocation such that everybody agrees with this allocation. That is severe shortage. I'll skip this slide. Then we can make our life even more difficult. Yeah. Let me see. Ah, yes, just to see whether you're still awake. I have a very difficult question for you. This point f tilde, so this is question 5 from the poll. This point f tilde, is it actually the same point in the function where the function goes from convex to concave? This is a very difficult question. So this is for the hardcore people among us. So at some moment, this function goes from here. It starts increasing, it keeps on increasing, but it increases less. Is that exactly this point over here? I will not blame you if you don't know the right answer. But actually the majority of you was wrong, because it is not. Why is it not? It is very close, but it is not the same point. What you see over here is that the point, this turning point, is already a little bit earlier. It is already over here, yeah? It starts to increase less and less, but still the average slope becomes more and more. And at some moment, it also becomes less, yeah? I think that this is a very difficult question, but I just wanted to let you know that in a convex concave return function, you always have a turning point. But this f tilde is not the same point. It is slightly more to the right. Yeah? Think about it. Okay, then even more difficult notation. If you understand 50% of it, I am happy. So what we have over here is we have two different countries, the Netherlands, Germany, for example. The dose optimal vaccination fraction, F1 tilde, for the Netherlands is over here. For Germany, it is over there. Now we're gonna define another unique point. It is the unique point for the Netherlands. Yeah. So what you see is that the average slope of the Netherlands in this dose optimal vaccination fraction over here, it is higher than the one in Germany. Yeah. Now we're gonna continue. We're gonna continue over this line, yeah, from the Netherlands, and we stop up to the moment that this slope of this function is exactly the same as the slope at the dose optimal vaccination fraction of Germany. That is our second definition in this graph. I hope that it's clear to you. So what you do is you have two countries. You look at their dose optimal vaccination fractions, F1 tilde, F2 tilde. You look at their average slope. One of them has a bigger average slope. And with this one, you're going to continue until the slope becomes exactly the same as the average slope over here. So the green dots over here have exactly the same slope as the green dots over there. Okay. So we looked at the case with severe shortage. Yeah. Now we're going to look at the case where there is a lot of supply. There's a lot of supply of vaccines. What can we say about that situation? And that is the following situation, sufficient supply. So what is written over here, that is very complicated, but let me explain it by means of this example. We're going to consider the situation where we have enough resources to give the Netherlands at least this amount, the 0.5 amount of vaccines, and Germany at least this amount of vaccines. Or we have even more vaccines, but the Netherlands can get at least this, and Germany can get at least that at the same time. This is the situation that what we're going to look at. Suppose that that is the case. Of course, it does not need to be only 2 countries. It can be 100, something like that. Yeah. And suppose that we have so many vaccines that they can get at least this. What is then the optimal solution? And I will try to give you an intuition for this optimal solution. What you're going to do is you want to keep those slopes exactly the same. So first, you're going to give this amount to the Netherlands and that amount to Germany. Then you have some left over. And this amount of vaccines you're going to give to the Netherlands and Germany at the same time, while having the slopes the same. Yeah. So we're going to give the Netherlands a bit. Yeah. This results in a new slope, slightly less than the green one. And we're going to give Germany the same. We need to give Germany even more maybe. Yeah. Until we have exactly the same slope over there. So we're going to give resources while keeping the slope the same. And why is that? Because then the health benefits that you get per resource is the highest. So this is the optimal solution. So the optimization part, how does the optimization part look like? Well, everyone gets at least the dose optimal vaccination fraction in such a way that the slopes of all the countries are the same. That is the optimal solution. This is how you need to divide your vaccines if you want to get an overall optimal solution. Well, in case you're interested in it, you can have a look at the proof in the paper. What you basically do is you're going to look at an upper bound of the function by making this function concave. How do you make this function concave? You look at an upper bound. So you start with this red line and then you continue with the blue line. That is the idea of the proof. Of course, it's more complicated than I say now, but at least this is the idea, and that's what we call an upper concave envelope. Okay, so we know the optimal solution. We need how to allocate the vaccines. Yeah. Then we know the optimal solution. How should we pay the countries for the vaccines? What should the market price be? It is exactly this slope again. So in the end solution, you filled the Netherlands maybe up to here and Germany somewhere over here with the same slope. And this slope is going to be the market price. And if you use this market price, then the market allocation is in the core. Yeah. Okay, I wrote down an idea of the proof over here, but I will leave that for you for later. So if we look at this slide, what did we do? We looked at a certain situation, the situation where there's sufficient amount of vaccines. What is the optimal solution? How should we divide the vaccines? And how can we make everyone happy? What price do people need to pay or get for the vaccines? So again, we showed that there is a core element, namely this market allocation, yeah, and thus the core is always non-empty. So you can make everyone happy with your cooperation. Okay, then I have another situation over here, but given the time, I will skip that one. What I try to make clear in this slide, quite often we get a question, okay, nice, but actually cooperation also costs money. So you cannot cooperate without, I don't know, without transportation costs, without organizational costs, etc. And what I try to make clear in this example, okay, if either the costs are, we have fixed costs, so we have a fixed amount of money that it costs for the cooperation, or there are specific costs, it doesn't matter. If the core was already non-empty, then it stays non-empty. So in other words, what I want to make clear with this slide is all the results that we saw before, where we didn't include any cooperation cost, it is still valid. So you do not need to worry about those cooperation costs. Okay. Then a case study. This case study is data from 2009. Actually, it would be nice to get some new data about our COVID-19 pandemic, but this is from the Mexican flu pandemic. And we looked at the following data. We had 10 geographic regions from the United States. There was an epidemic in different stages. So in some stages, it was already in the beginning, the epidemic. In other stages, it was already quite severe. And in the initial distribution of vaccines was proportional. So the World Health Organization decided that everyone gets the amount of vaccines that's proportional to the number of inhabitants. What we did is we did some experiments. We wanted to see whether going from this initial distribution from the World Health Organization to an optimal solution that we find with our optimization problem, whether that is possible. Of course, an optimal solution is always better, but can you always make everyone cooperate? Is the core always non-empty? Yeah, we did that by varying the amount of vaccines and by varying the time at which vaccines were available. And we got this figure. Okay, so how should we read this figure? So we did several experiments, yeah? And over here, or on the horizontal axis, you have the moment of vaccination. So when you start vaccinating, in which part of the epidemic, already in the beginning or later, etc. And here we have the total number of vaccines. And does this actually correspond with our theoretical results? And actually it does, because you remember, we started with severe shortage, and the severe shortage is exactly over here. Yeah, there are not a lot of vaccines. And then we found a non-empty core. That is what we proved, right? That was the first proof. Then, with the sufficient amount of vaccines, that was the second part, where we have a lot of vaccines. That is actually over here. And then the core is also always non-empty. Yeah? And what happens in between? We don't know. We didn't draw any conclusions yet. It can be that the core is empty. It can be that the core is non-empty. So in between, that is still something to look further into. What happens if we have, I don't know, not severe shortage, not a lot of vaccines, but something in between? What happens then? So we didn't draw any conclusions, but what we did see in our results, that if the core is not empty, then quite often a market allocation belongs to the core, but not always. And then what if we go over this moment of vaccination? So you see that the later the moment of vaccination, the more down those blue squares go, right? So the earlier we have a non-empty core. Why is that? Well, it comes from this S-shaped return function. So the later you are, in with vaccinating, yeah, the later you are in your S-shaped return function. And remember, it was a convex concave return function. So the later you are with vaccinating people, then you are later in your S-shaped return function. So maybe you're only in this concave part of the return function. And that was exactly the return function from Shapley and Shubik, where they showed that if your return function is a concave utility function, then the core is always non-empty. And this corresponds exactly with their results. Okay, so let's try to draw some conclusions. Well, first of all, I gave you an introduction to cooperative game theory. I hope that this was clear. After that, we looked at our application. And we saw that this application with vaccines was a resource pooling game with S-shaped return function. So we want to distribute the vaccines, and everyone, the utility that they get from the vaccines is an S-shaped return function. I also wanted to make clear to you that cooperation is a delicate matter. Of course, if you look from a joint point of view, then it's always better to cooperate. It's always better to give away resources, etc. But does everyone agree with that? Is the core non-empty? In that sense, cooperation is a delicate matter. You cannot always assume that everybody wants to cooperate. Yeah. Then we saw that the core is non-empty when we have very few or a lot of vaccines, so severe shortage or sufficient supply. And we saw that this market price allocation, that everybody pays the same amount of money for the resources, that this allocation is quite often in the core. Okay, then thank you for your attention. And I hope that you learned something from it. And I think I should give the word now to Noor.
Yes, thank you very much, Marieke, for this very interesting presentation. I think all of us found it very good that you started off with like nice examples of the different sharing models, and especially also with the COVID situation where it's about like sharing and how do we distribute the vaccines. We got some questions in the Q&A. Also feel free to hit up other questions if they still pump up. We have like 3 from Ahmed. He's wondering, hi, is it possible, can we use term possible outcomes instead of possible relations? Possible outcomes is more intuitive, is in probabilistic sense, I guess. Please guide me on this.
I see the question here as well. Honestly, I'm not sure what is meant with this question.
Maybe
possible relations. I'm not sure.
Maybe we can also.
Can we ask him or her?
Yeah, Ahmed, feel free to like maybe explain it in the chat. We have one answer from Laurent. He was talking about the subsets of the set.
Do you mean that you mentioned that the possible relation in the first row? I'm not sure. Do you maybe mean the following thing? Let me go back to the slides.
Yeah, Ahmed also said you mentioned that the possible relations in the first row of the table.
Yeah, okay, I think now I see. Let's go back to the ice cream example. So maybe, Ahmed, do you mean this, that maybe it is not possible that Alice and Bob cooperate? So why should we include this coalition Alice and Bob over here?
You can give it a thumbs up if it's that what you mean.
So that maybe, I don't know, Alice and Bob, they are in a fight and they do not want to cooperate anyway, even if they can get ice cream for it. But if Carol is there, then the three of them can cooperate. So that we should not include this A, B over here, but we can include the A, B, and C over there. Yes, okay, yeah, that is a very good question. And actually that is also one of the things in cooperative game theory that's called restricted games, where you have an underlying graph. You have an underlying graph with the players, and you draw a line between those players if they actually can cooperate, yeah, or whether they are in a fight or not. And based on this graph and based on this game, you actually get a new game, a so-called restricted game, where you indeed include only the possible coalition. So not every coalition, but only the possible coalition. So that is indeed possible. You're very right, very good.
Okay, I think it's indeed because Ahmed also responded. It's what he meant.
Okay, good.
He also posed another question. This triangle interpretation was shown in the previous lectures, but when we have, let's say, 10 players in glove game, it's the second question.
Then you cannot draw then you cannot draw a triangle. Indeed, you can only draw a triangle for a 3-person game. For a 2-person game, you can simply draw a line, basically. For a 4-person game, you already need to draw something 3-dimensional. So it always has 1 dimension less. So here we have 3 persons, and how we draw the core is in 2 dimensions. If you have 2 persons, then you need to draw something in 1 dimension, which is a line. So if you have 4 persons, then you have to draw something in 3 dimensions. Then it already becomes more difficult. Then you simply cannot get the core by means of drawing it. Then I would recommend you to look at the constraints, try to write some linear program for it, something like that. Then you need to do something more sophisticated in mathematical terms.
Okay. Then we have another question from Zia. It's wondering, given that the market allocation is the core in vaccine distribution, how would you say that the health institutions use this information?
Good question. So how can they use this information? Well, they can use it, for example, by still having, let's say, a decentralized solution. So the World Health Organization can, for example, say, okay, listen, we calculated the following thing. This is the optimal solution. So those vaccines need to go to that country, yeah? And this is the price that needs to be paid for that. So that the institutions can use this price, this market allocation price, as a price that needs to be paid by other countries. Is that an answer to the question?
Let me quickly check the chat. I think it was a clear answer. We don't have any questions anymore in the chat, I see, or in the Q&A. Are there any more questions? You can still... Yeah, Zia answered yes, hence why NL gave vaccinations to Eastern European questions a while ago. Thank you for the clear explanation.
Okay, good.
So yeah, I would say we don't have any questions anymore. So we can, yeah, thank you for this really good presentation. I would say then we continue also next week for the ones that are still here. Next week there's no lecture, but we will start Thursday after. So then we're back again with another lecture. So thanks, Marieke, for this great presentation. Thanks for these nice examples. I think we all learned a lot today.
You're welcome. I hope you enjoyed it.
Yeah. We got a lot of thanks in the chat, so I think.
Okay, good. Well, looking forward to the next presentation.
Okay. Then goodbye and have a nice evening, everybody.
Okay, see you. Bye.